Hello everyone and welcome to SydneyAlt.net February. So if you're here, please put a comment in the chat so that we know that we've actually got people that we're talking to. Let's see. And we've got Francis here as well, and very excited to have Jim Webber all the way from the UK, where it's bright and early. Wow, all right, we've got George there. Good. Give it a minute or two to have a few more people come in. We've got Francis, that's good. Now, I'm wearing the SydneyAlt.net t-shirt that Francis made here, but Francis
is wearing the JetBrains
t-shirt.
But we better cozy up to the sponsors.
Actually, JetBrains sent me a survey recently, so hopefully the program will continue. I answered that I thought it was very valuable to give away free licenses, very valuable for the group. So I hope it continues. Let's see. Give it one more minute, and then we'll start. Oh, you are in the Twitch, Jim. You made it.
I sneaked in a different browser tab, but once I start presenting, I'm not going to be able to see the Twitch. So if anyone is like giving me shit in Twitch, you have to let me know, James.
I will.
I know that Australian audiences are famously inquisitive, let's say. So any of you guys give me a hard time, James will police you.
I was going to say I just passed the messages through directly.
That also works.
I thought if anyone could handle some heckling, it'd be you.
Oh, thank you. It's very kind of you.
Having it being like early in the morning, one coffee in, time for some heckles with some Australians. All right, I think we're good to start. So what is it? 7:05, just about. So. Well, I'm delighted to have Jim on the show. So Jim recruited me to ThoughtWorks, I don't know, like 15 years ago, probably too long to remember. And we had many nice pub visits and the odd project and some conference presentations and such like together. But since then, I think by then you'd written like 2 books or something, like a REST book maybe and a web services book. And it was exciting REST days in those days, but now Jim has moved on to like Neo4j, and I mean it was distributed systems, right, as well at that time. So I mean Jim has presented at what, hundreds, if not thousands, of conferences. Do you think?
I don't know. I mean, it beats doing real work, right?
It certainly has more flights and hotels involved.
Certainly does.
And more meeting people. So yes, he's quite a famous presenter, and he's also pretty funny too. Not to make it hard on set the expectations too high, but yeah, this is also a pretty solid topic. So pay close attention so that you can follow along. And we've got things to give away at the end. So we have got 2 JetBrains licenses to give away, and we have also got 2 programmable tickets to give away. And we don't have a programmable t-shirt. I should have brought one in. I've got one.
Yeah. Yeah.
I'll put a link in the chat shortly for the programmable conference. But that's really quite a prize. It's a 1-day conference and it's quite a lot of fun. There's some interesting stuff there, and each year it seems to keep getting better. So I'll put that there, and I'll ask you 4 questions at the end for these giveaways. All right, Francis, anything you want to add before we go to Jim?
No, nothing. I think, yeah, I think I'm really excited about the subject matter. I think you rarely see people talk about distributed systems, yeah, just as a topic these days. So, yeah, I'm quite curious to see what Jim's got to say about this ever evolving subject matter. Yeah, absolutely. So
All right. Oh, shall I add your talk on, Jim? Put it on the stage.
Sure thing.
Here we go. I'll put you at the top because you are the important one here.
Thank you very much. I'm actually going to hide the browser now behind PowerPoint. So this is the last I'll see of me and you for a few minutes. Hello, everybody. Thank you for coming. Thanks for choosing to spend some of your evening talking about distributed systems. I think Francis is right, actually. We haven't talked about this for a while. If you're, you definitely should be in the pub for this, by the way. Unfortunately for you, it's evening, so that's permissible. If I was in the pub at this point, it would be worrying. But we haven't talked about distributed systems, it seems, as a community for a long time. There was a kind of a peak of interest, maybe, I don't know, 10 years ago or so, when people were talking about NoSQL databases, if you remember that. And there was a lot of hoo-ha about this thing called the CAP theorem, kind of Brewer's CAP theorem, which tried to kind of give us a framework for reasoning about consistency, availability, and fault tolerance. And people were really into that, right? It was like a real explosive a topic of discussion for a while, and then, as happens in IT, the trends moved on, and that kind of went back to being a more quiet, contemplative part of the computer science landscape. And the reason I'm talking about this today is that I just think it's still really interesting. Distributed systems are really fascinating. They're like such a crazy multidimensional puzzle that they're quite interesting to study, and they got a lot of practical uses, right? I mean, you're probably all very used to deploying, kind of huge Kubernetes-based systems where you've got lots of moving parts. But I think one of the really interesting genres of distributed systems is where you're trying to coordinate computers to work together. And it turns out that's a really hard problem. It doesn't sound hard, right? Because we've got computers, they're connected via networks, they talk to each other. It should be a very easy problem. But it turns out it isn't. And I'll tell you a personal story. So, and this isn't me flexing, right? Honestly, but there's a bit of personal background. So I come from kind of a blue collar background, working class background. And I was the first person in my family to attend university. In fact, I was the first person in my family to get any qualifications. So the lovely thing about that is that my mum thought, past tense, thought that I was wonderful, right? The kind of smart son. And so at one point she asked me, like, Jimmy, because she gets to use the diminutive. None of you guys get to use the diminutive, right? Jimmy, she said, what are you doing when you're playing on them computers? Because obviously computers are for games. I said, well, Mum, I make computers like agree. And she said, oh, I don't really understand. Can you tell me what that means? I said, well, imagine that I've got two computers, and in one of them I want to store a number, and I want the other computer to store the same number. And she said, what do you mean? I said, well, let's say I want to store 6 on this computer. I want to make sure that 6 is also stored on the other computer. And she looked at me and said, wait a minute, like with your degree and your PhD and blah, 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 you make this computer store number 6, yeah? And then this computer stores number 6. Uh-huh. Can it store any number? Can it store 10? Yeah. So you can make this computer store 10, and then this computer will store 10. I said, yeah. And that's what you've had to go to school for like 100 years. Yeah. And she looked at me, she said, oh. And that was heartbreaking, right? Because in her world, it's obviously so simple to make two computers store the same number. And in fact, when things are going well, when there are no faults, when there are no race conditions, when there's none of this real world stuff, making two computers store arbitrary values is straightforward, including the number 10. You can make two computers store 10 really easily. But then what happens when one of those computers temporarily or permanently fails? What happens when there's a network glitch? What happens when messages are delivered slightly out of order? And all of these things come to the fore in distributed systems. Now, they're easy enough to solve if you're willing to make your systems unscalable. But they're really difficult to solve if you want your systems to have a good degree of scalability as well. And what we learned from the CAP theorem stuff from 1,000 years ago is that typically correctness and scalability are enemies of each other. You can get one, but it's hard to get the other at the same time. And what I'm going to show you this evening is it's a protocol. Ultimately, we're going to see a fair few protocols this evening in a humane way. But I'm going to ultimately finish up this evening with a protocol that gives you safety, so the ability to store numbers, if you like, to store data on many computers safely, but also allows us to have great scalability. And of course, this works pretty well in my day job. In my day job, I work on databases, and we want databases to be both large and correct and scalable. So it forms the kind of underlay for future versions of Neo4j. So if that's your thing, if you like a good protocol, then you're in the right place for the next kind of hour or so. So how's it going to go? I have to apologize. We're going to talk about ancient Greece and why that sucks. We're going to talk about this remarkable quality that humans sometimes have called empathy. And then we'll flip over into my day job, which is a little bit about graph databases. And I'll tell you about a protocol called Riot that we've been working on at Neo4j, and also in collaboration with some folks at University of Sydney and a professor at the University of Berkeley, and tell you how that works. It's quite interesting. Hopefully it's quite interesting. So first, the apology. The title of this talk was the Pub Time Parliament, and it's a pun. It's probably a crap pun, to be honest, but in distributed systems, we all know this really famous paper called the Part-Time Parliament, and it's where an incredible computer scientist called Leslie Lamport, and Lamport basically invented everything about computer science, right? He was one of the original kind of grandfathers of computer science. His fingers are everywhere in our discipline. And he wrote a paper called the Part-Time Parliament, very famous. And it was an early paper about how you can get computers to agree with each other, even when there are faults and failures and people dip in and out and so on. And I have to say, although Lamport is a million times better computer scientist than I will ever be, I hate this paper. It's a really good protocol. It's actually a protocol called Paxos, which many of us will have heard of. But it's kind of crap, because in his world, as we'll see, Lamport talks about this very reified, this very gentrified kind of domain where Greek senators propose motions to one another and ultimately agree. And as we know in the modern world, computer systems are not like that at all. There is no calm or decorum. Computer systems, production systems that we depend on, are big and chaotic and insane and have unexpected behaviors. And it's very much more like a pub than it is a kind of debating society. In a pub, there are things that are happening that are fine. You know, you're a couple of schooners in and you're having a nice chat. My mate Stevo has been in the pub since 3 p.m. and he's plastered and falling off his bar stool. He's in a failing situation. James Crisp has just gone and done a tactical chunder in the bathroom, but now he's recovered because he's got it, you know. Did I get that right, James? I think so. There's a sheepish grin. There's a sheepish grin there, right? But it's chaos. And so everyone is either in a state of being fine, crashing and recovering, or crashing permanently. Add to that the cacophony of background noise that's going on, right? I mean, I habituate your pubs in Sydney. They're not quiet places, right? This is chaos. And this is a much better metaphor for the world that we live in of distributed systems. Things are chaotic. So, what does this mean for us in .NET world? Well, it turns out we've had things called transactions in .NET for a long, long time. Even when I was an aspiring .NET programmer under the tutelage of James Crisp, then we had this kind of ability, right? And this was a long time ago. For what it's worth, it's always been my ambition to be a .NET programmer. And then I keep getting shunted into this thing called Java that you might have heard of. But anyway, I do know a little bit about transactions in .NET, and it's kind of nice, right? You've got a bit of boilerplate, right? But you've got, if you're talking to a database, something like SQL Server, because I'm old school, right? You've got some boilerplate, and this literally says, hey, we're going to start a transaction here. And a transaction is a unit of work that's either fully completed or logically appears never to have executed. So it's a really nice metaphor, right? Because you never leave your underlying database in an inconsistent state. And look, those of you that really know databases know that databases are always in a terrible inconsistent state because isolation levels are insane. But Francis, we're coming on to distributed transactions in a moment. We are going to address your nightmares, I promise. But what happens, right? So you start a transaction and then you do stuff, right? You manipulate state. You kind of maybe you serialize your object graph into SQL and you write it into tables and so on. And then if something goes wrong, if the database says, oh, sorry, you violated a constraint or I've run out of disk or something like that, it rolls back. And it's like, oh, well, I mean, that didn't save properly. But actually, now it's all clean. We're in a clean state. Maybe we can try that again, or maybe we could ask the user to help. Yeah, whatever. But the nice thing is your database is still in a perfectly good state at this point. But of course, and something that sadly my mom didn't understand is while you're going backwards, you can still fail. So even when you're undoing your work, you can still fail. Now, it turns out typically this isn't a problem in practice. For example, in Neo4j in the database I work on, if a transaction decides to roll back, we just release a chunk of memory. So actually this isn't significant for us. But the point here is that stuff can still go wrong when stuff is going wrong. And that makes distributed systems hard, because you could have James doing a tactical chunder, coming back to life in the pub, and then actually still going wrong. I'm making you out as a terrible alcoholic / lightweight here, James. I'm sure that's neither of those are true. So stuff can still go wrong when stuff is going wrong. And this is just working with one database, right? This is the kind of stuff that's bread and butter for you folks, right? I'm sure you've written 1,000 projects with code that looks somewhat similar to this boilerplate. But then you can go one step further and say, actually, committing to one database is good. And it's really nice that I've got this transactional glue that makes it safe to talk to one database. But in practice, for production systems, having one copy of the data typically isn't enough, right? You want multiple copies of the data. Sometimes you even want to be able to persist different things to different places. You might want to store something in a relational database and enqueue something on some transactional queue. And that means you have to do a distributed commit. That means a commit that not only does commit on one machine, but has some protocol that runs to run the commits or rollbacks on lots of machines. And of course, unsurprisingly, Microsoft are quite good at this. They've got a distributed commit thing, right? So this is slightly more complicated than the previous slide, but it literally just says that we're going to start a new transaction and we're going to make it mandatory. And we have one participant here, so using a particular connection to a particular machine, we do some potential work there. We've got another machine, another SQL database, say here, and we're going to do some other work there. And then at some point we commit, right? We say, okay, we've finished doing both sets of work. And when we do that, we're asking the underlying infrastructure, which is some kind of protocol, actually probably something like the two-phase commit protocol that we'll see in a minute. And some talking happens, some discussion happens between the servers, and then they will say, yeah, we're both happy to persist this work forever, and they persist, or one of them or both of them say, I'm not happy to persist this, and they will abort. So you can kind of spin the wheel, and then if something goes wrong, you catch the exception and say, oh, sorry, we couldn't commit that across both the machines, right? And there's a lot more depth here than perhaps I've alluded to, but basically that's how it works. You ask the machines, are you happy? Yes. Are you happy? Yes. Everyone's happy. Let's go ahead and make this durable, as we say. That's the D in ACID, right? So how is that implemented? Well, it's implemented typically through a protocol called two-phase commit. And two-phase commit is like the granddaddy of all distributed systems protocols. And there are two roles. There's a privileged special role called the coordinator. And the coordinator's job is to create elections, effectively orchestrate votes. And so all of the, let's say they're all databases in this system, the coordinator's job will be, when invoked, to say, hey, all of you databases out there that have participated in this transaction, transaction one, are you happy with it? And if everybody writes back and says, yeah, we're happy with one, then the coordinator tells everyone, let's commit. And it's really nice. It's really nice. It's the classic protocol. It's actually written in 1976 by some very famous computer scientists, including Stonebreaker, who's very famous, of course, in relational database world. And it's very straightforward, but it has problems. It has really nice features that you get an atomic commit, like either everyone commits or nobody commits. That's really nice because it keeps your system kind of together. But you can see problems. Like for a start, the coordinator is a problem. What happens if your coordinator goes slow? Well, then your whole system goes slow. What if your coordinator crashes? Jim, if a coordinator crashes, we'll simply replace him with a new coordinator. Oh yes, but one of the unfortunate things is you can't in distributed systems distinguish between a slow process and a crashed process. There is some earlier magic here called FLP, which predates the CAP theorem. And FLP tells you basically distributed systems don't work. You're lucky as humans that they are up for long enough that you might get some useful stuff out of them, but that is a time window when you're just fortunate. And strictly speaking, distributed systems do not work. So FLP, it's Fisher, Lynch, and Patterson. It's a paper about if you have a distributed system, or in fact any asynchronous system, if you have one faulty process, the whole thing turns to shit. That's slightly eliding some of the detail there. But you can see here that if the coordinator fails or goes slow, the system goes slow or doesn't make any progress. And that's bad, right? Because computers are about making progress. They're about processing things. Worse, if you're halfway through a transaction, so if you've done the first phase of the commit and you've voted, hey, I'm happy with this, maybe you're using a relational database and you've locked a bunch of rows. And those rows will stay locked until the coordinator says, let's commit now, or let's abort. So you're in limbo. And what if one of those rows happens to be representing a popular product that you want to sell from your warehouse? Well, now you've just DOS'd yourself, right? That's a problem. And you've also got single points of failure. The coordinator is a single point of failure. And if you want to make the coordinator fault tolerant, you have to coordinate the coordinator. And you can see how this ends up being turtles all the way down, right? So it has problems. Now, a really bright computer scientist, one of my favorite computer scientists, Heidi Howell. Heidi is did a PhD at Cambridge in the UK, now works at Microsoft Research. And they went back and looked at this because, as I mentioned earlier, so Chris and Heidi looked at this. They looked, two-phase commit's really nice because it has this atomic commit property. It's really useful, really easy to understand. But we don't like the blocking properties. When the coordinator dies, we don't like that. It causes all kinds of things. So can we change that? And so they wrote a paper back in 2024, and they said, actually, it's possible to take some of the coordinator state and share it with the participants, so that if the coordinator dies, and coordinators do die occasionally, you've got an expensive recovery path, which is to reconstruct the state from the participants, but at least you've got a possible recovery path. And it means that then you can also run two-phase commit really fast in the normal case. So while you've got no faults, two-phase commits quite fast. And then if you have faults in this system, at least you can recover from it by reconstituting state from the participants. It's quite a smart paper. So that means we're done, right? Problem solved. Two-phase commit revisited with universal two-phase commit solves the problem. So thank you for coming to my talk this evening. We are now finished with distributed systems forever. Hooray. Of course not, right? I mean, there's still stuff going on. In fact, I think we're at this fork in the road because there's a couple of useful things going on here. When I first did two-phase commit, I learned about transactions back in the year 2000, would you believe? My first job after grad school was in a middleware company doing atomic commit, doing ACID transactions, as we called them back then. And it turns out that I didn't realize at the time, but we're doing two things when we're doing transactions. One useful thing is actually replicating data. I'm saying, hey, James, could you store this? And hey, Francis, could you store this? And actually, if you think about it, that's me replicating data. I've just made two copies. But the other thing I'm doing is I'm carefully coordinating. Hey, James, can you store this? No. Oh, interesting. You can't store this. Maybe you're out of disk. I should probably tell Francis not to store it as well then, because I don't want Francis to have an update that James doesn't have, because then they're out of sync. So actually, I'm doing some coordination as well. So there's two things going on. And it turns out that we have protocols that address this. Now, Paxos is interesting. It's the Lamport protocol, the one that I named this talk after. And it's very famous because when Lamport looked at two-phase commit, after 20 odd years of two-phase commit being used, he noticed that the coordinator, much as Heidi and her team noticed, the coordinator's the problem. And if the coordinator dies, your system kind of grinds to a halt. And so I think that what Lamport's genius was here, he noticed that coordination is a role. It's not a server, it's a role that a machine can play at any time. And more interestingly, that means that that role can move around your cluster of servers. And that's really useful because perhaps if your original coordinator died, that role could move to another server that's still able to process. And you get this thing then called non-blocking consensus. So your coordinator dying doesn't stop you within fault tolerant limits. If you lose too many servers, you can't. But if you lose a minority of servers, you can still keep processing, right, without your users really knowing. And that's really nice. That's a really good result. And so what Lamport did, he wrote this paper called Paxos, and in his mind was this kind of Greek Senate, ancient Greek Senate, where some senator would stand up and propose a motion, and the other people would listen. And if that senator was up to date, that is, if he'd seen all of the other motions, then this motion would be debated. And if that senator wasn't up to date, if that senator had been asleep because he'd been on the Recina last night, then it would be ignored because he wasn't up to date enough. And so you can see how even the state of being a valid coordinator depends on your history and whether you're consistent with the other people. And that's nice then, because it can move around. But unfortunately, in practice, Paxos was poorly understood because the language was really difficult. Proposers and acceptors, there's a bunch of ancient Greek stuff and things like epochs and blah, blah, blah. And it was really confusing, which is a real shame, because if you dig down this idea of coordination being in a role and needing only general consensus, general majority, rather than an outright unanimity that two-phase commit demands, means you can typically make progress even when things are failing. Remember, in two-phase commit, if anyone fails, any participant or the coordinator fails, you can't make progress because it's unanimous. And Paxos said, no, we just need a majority to agree on a value. And there's a lot in here, but the paper was impenetrable. Neo4j, we used to have a Paxos implementation many years ago, and we thought it was the right thing at the time because basically there was nothing else. And we had about 20 engineers at Neo4j at that time, and I'm confident that we had at least 21 opinions on how Paxos worked. It was so confusing. And most of our support load, which was rising steadily, came from the fact that ultimately came from our Paxos module and bugs in there because it was a complex protocol. But for people like Lamport, it wasn't a problem. He considered Paxos to be perfect or at least good, and it is. After many years of study, it clicks for me. But Paxos had to, Lamport had to write another paper. He had to write a paper called Paxos Made Simple, which is basically him saying to the rest of the universe, why can't you just be clever like me and understand this? And I think this is important. He writes, in fact, it is among the simplest and most obvious of distributed systems. And that's awful, because he's basically saying, you guys suck that you can't understand this. I think it's very straightforward. And I'll point out that Leslie Lamport, as I said, is 1,000,000 times better at computer science than me. But he has that kind of bias that he thinks he's normal, and he's surprised that the rest of us mere humans don't understand Paxos. So he writes Paxos Made Simple, and in the introduction for this, he goes on to say, at its heart is a consensus algorithm, the Synod algorithm, which is like absolutely straightforward. And it isn't straightforward, right? It isn't straightforward at all, because at Neo4j, we found with Paxos that we had a quadratic or polynomial support load because we couldn't understand it. We didn't have in our team even a kind of agreed upon how Paxos would work. I remember all the arguments. Oh no, it works like this. Oh no, it does this in this case. And we were clueless. And the paper, the literature that we came to depend on was impenetrable, and so it didn't help us. And it felt like this was Lamport, you know what I mean, just telling us that he's a galactic mega brain and we're all stupid, and it felt bad. So I want to talk about empathy. And I know, for those of you that know me, you know I'm not Mr. Empathy. That's Dan North's job, to go round and kind of palliate all of your software projects. That's not me. I'm the angry guy that gets angry about stupid computers and stupid people who use stupid computers. But there is an element. I know, right? I was an excellent consultant. You can see why I was in that business for so long. But there's something here about empathy in distributed systems.
Jim was an excellent consultant, by the way.
You are. The check's in the mail, mate. Thank you very much. My superpower was being angry at stupid people, and it's not a sustainable consulting practice. But empathy is important in software, right? We know this as software people. Like, this idea of being kind to your team or being kind to your future self, right? So don't write shitty, hacky code. Make the code read nicely so that it's, the variable names and the method names tell you very clearly what's going on inside the code. All of that stuff that we've been learning for years and hopefully take somewhat for granted. But that's even more important in distributed systems. And the reason is, in distributed systems, there are weird transitive places where bugs hide. And if you don't have empathy, if you build a complex, sophisticated beast, as Paxos was, you're going to get subtle bugs in there that are going to bite you on the ass at exactly the wrong time. It's going to blow up at 4 a.m. in production because a bug that you had no idea could possibly exist, the cogs line up in just such a way that click, and now your whole system shits itself, to use the technical computer science terminology. So empathy is of critical importance when you're building resilient systems. And one of the things I like in terms of empathy is this protocol called Raft. Raft came out of Stanford in 2014. And Raft is not the fastest protocol in the world. It's not the most sophisticated protocol in the world. It's not anything except for one thing. When Diego Ongaro and John Oosterhout, and some people on this call are old enough to know John Oosterhout because he's the tickle guy, right? He's a complete polymath. He's awesome. Like, he's a mega genius. But they found when they were teaching Paxos to their class at Stanford, and Stanford's a respectable university, right? The students weren't understanding it. And in a way, I'm relieved, because we at Neo4j clearly didn't understand it that well either. And we're not even students. But he was, Oosterhout was teaching, and the students weren't understanding Paxos. And he said, well, that's a problem, because these students will grow up to be practitioners building perhaps Paxos, and they'll build it wrong because they don't understand it. And it's not their fault, because they're bright students, right? To get into Stanford, you have to be, this bright. And so he decided to, with his student Diego Ongaro, to wonder about what would happen if you built a consensus algorithm, so an algorithm that makes computers agree, but instead of optimizing it for the computer, you optimized it for human understandability. And the result was a protocol which is quite famous now, called Raft. And Raft's interesting because it makes a whole bunch of simplifying decisions. For a start, its name. What's Raft? Well, a Raft is a bunch of logs tied together. By the way, I was working on the Raft implementation for 3 years before I understood that pun. But it turns out that in Raft, you don't agree about a value. You agree about a log. And the lovely thing about a log is if we agree on the nth element, inductively, we must have agreed on the n-1th element. So it's now simplifying. Also, as a database person, we live in a world of logs. Underneath every database, there's a log. It's typically a write-ahead log, which is really important. It's where we write the things that, where we write the changes that we'd like to apply to the database. So Raft composes really nicely with databases. But it also makes a bunch of other simplifying assumptions, clear roles, leader and follower, shared log, not independent value. So you're always agreeing on a log. Everything's just decided by a majority. There's no other way of deciding in Raft, even though mathematically other options are available. And you've got this idea of being very leader based. So a single leader makes all of the decisions, and everyone else, if they're in a good state, just copies that leader's decisions. And also Raft handles everything. It's a distributed system in a box. It handles membership of the cluster. It handles election and re-election of leaders as failures happen. And it handles data replication as well, right? So it's really, really nice. That paper, by the way, that you can see in the right there, even if you're not a fan of like computer sciencey stuff, that's probably the friendliest paper in computer science history, and it teaches you a lot about distributed systems. It's actually well worth a read. So Raft, when we built it back in 2015 through 2016 at Neo4j, we used it to replace our existing Paxos implementation, and our support load changed from like insane, unsustainable to minimal. which was really nice. And it turns out one of the reasons is that everyone working on that implementation, and at the time there were only like 5 of us working on it, we understood it. And we could point to this paper and say, oh, this Java code works like this because of section 3.2. And it was very understandable. So how does it work? A little cartoon, got a bunch of servers here. They're all talking to each other, and their job is to just fill in the log. So at the moment, server 1 is the leader, and it's sending out proposals. It's saying, hey, can everyone else append this value at the ith element of their log? And if they can, the other servers are responding back saying, yes, I can. And then server 1 is saying, okay, we commit, we move the commit pointer, and then we repeat. And at some point, you know, you saw for a moment there, server 1 died, and server 1 lost its leadership. Server 5 won a leadership election because it was the most up to date, and then they carried on. Right, there was no stopping. It's a non-blocking consensus protocol, and that kind of thing is really useful because in real systems we don't want to stop when one server dies. And so on this cartoon goes. It's a really nice thing. But I think what Raft really taught us is be nice to each other. Everything about Raft is suboptimal. And I see all these fancy computer science people, they are kind of beating up on Raft. They say, oh, well, Raft uses a majority. Well, you can do better than that mathematically. And in fact, here's one of my favorite computer scientists again, Heidi Howard. Her PhD was all about being able to have safe quorum, so votes, with a minority of participants, which sounds kind of weird, right? Because how can you have a safe vote with like 1/3 of the people voting and 2/3 of them not being involved? Sounds a bit weird, but look, I live in the UK where our parliamentary elections are performed under a system called first past the post. The current government has a stonking majority of about 2/3 of the seats in parliament, and they received only about 30% of the popular vote. So even in our human world, we can see how these things are possible. But Heidi did this mathematically, and it turns out by arranging your servers into trees or tables or columns or whatever, you can get fewer than half the votes and still mathematically have a safe outcome. The problem is that the thing that you pay for there is that then the machines aren't equivalent. Depending on your position in this quorum, you're more or less important. And at 4 a.m., when the bleep goes off, that's really hard to debug. You're not being awesome to each other. You're being clever. So if you ever have to choose between anything except safety and simple, always choose simple. That's what Raft taught us. And that's really something that when I was working on the new stuff that I'm about to tell you about, that we really took to heart, because we don't think you can create a protocol that will be bug-free and useful unless normal people like us on this call can understand it. Lamport can understand anything. We're more normal. We have to be given humane things that click with us to help us to understand. But then there's also scale. Right now, Raft, it turns out, is really fast. The benefit of Raft is that you've got one leader making all of the decisions in its own process, in its own memory space, and then in a good situation, everyone else just follows. But you've got one leader, which means in practice you've got one write channel, and people get upset about that. Sometimes for academic reasons, they think the architecture won't scale, and sometimes because generally they've got such high write throughput that one leader isn't enough. And so you want to be able to have multiple leaders potentially. But now if you've got multiple leaders, you have to somehow coordinate between them. And that can get expensive, right? So there's this tension between scalability and safety. And we always want to be safe. And in my world, what can happen is users build fancy graph models and they want to scale. Now, graphs are lovely. For those of you that haven't picked up Neo4j, I promise this isn't like a sales pitch, but I really like graphs. They're a really lovely model. It was the thing that I left ThoughtWorks for because it made sense to me. It makes sense to you folks because the first thing we do when we're building a system, even in .NET world, is we go to a whiteboard and we start drawing bubbles and sticks that explain the kind of fundamental entities in the domain and how they interact. And a graph database literally stores what you've drawn on the whiteboard. We store it in the database. So we don't denormalize it into columns and rows and all that stuff. We just say, okay, here's an entity that rookie 333. My first Neo4j job was also unpaid because it was open source contribution to Neo4j. So I'll buy you a schooner the next time I'm in town and we'll cry on each other's shoulders about unpaid labor. But it's a lovely thing, right? You connect these things together. I can say Jim is a friend of James. James works at ThoughtWorks. Jim worked at ThoughtWorks. Jim moved to Neo4j. All this kind of stuff. It's really humane. But what's really interesting is, from a distributed systems point of view, any two nodes or any two entities in the data model can be connected together via a relationship or an edge. And that's really very straightforward in Neo4j today because we've got a single memory space model. So it's just a pointer. But what happened if I wanted to put, say, Jim and James and Francis on different servers for load balancing reasons? Well, now I've got an edge, a relationship that spans servers. And so now any updates, say, between James and Francis would have to go to at least 2 servers. And I've got to coordinate that. But coordination is the enemy of scalability. So it gets kind of complicated because users want big graphs. Despite that, they don't want their graphs to be corrupted. Like a database shouldn't corrupt, and they want it to be fast. And we can't lose this. Any two nodes can be connected by any number of relationships of any type, likes, follows, works for, owns, blah, 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 in any direction. And that's something that Neo4j users really value because it helps them make really high fidelity data models. And so anything that stores this data has got to be respectful of this data model. But distributed systems distributing Neo4j is hard, right? Because you'd like to do something like two-phase commit because that's really safe, but you also know that will inhibit scalability. That would give me one transaction at a time scalability. And that's no good in a modern system where even at Australia scale, I may have tens of thousands or hundreds of thousands of concurrent users battering away at my system. And if you upgrade that to US scale or China scale, it's an order of magnitude even harder, right? And so there's that tension there. And worse, in graphs, there's this idea of reciprocal consistency. So if I follow you on Twitter, if people are still using Twitter, then you have to know that you are followed by me. And if we're on different shards, any updates to that relationship, that follow relationship, have to be reflected on both sides. And they have to be reflected on both sides in the same order. And if that doesn't happen, then you get corruption, where I think I follow James, but James doesn't see that I'm following him. And then he gets snooty with me and denies me the job that I applied for because I don't follow him on Twitter anymore, right? Or he launches the missiles or whatever. And so there was a piece of work by Paul Essel-Chelvan that modeled this, and it said if you don't get that right, any busy database will become garbage in a matter of months. If you're wondering, by the way, why Rosa and Antonio rather than Bob and Alice, it's because I like to use the names of historical socialists when I'm writing books, and then I sell it to Americans. And that is the way that we gentrify them. So that's Rosa Luxemburg and Antonio Gramsci, if you're interested. But it works, what it really means is this, right? I've got 2 transactions, T1, T2. T1 is going to delete the relationship between Karl Marx, obviously, and T2 is going to add a property, add some data to that relationship. And the question is, after both of these things have executed, how does the database look? I'll give you a moment to puzzle it. Yeah, I can see James furrowing his brows slightly. That's a good sign. And the answer is, I have no idea. And you don't have any idea. It can go one of a few ways, right? If T1, if they happen to be processed in the same order, either the relationship exists or it doesn't exist. If they're processed mutually out of order, maybe the relationship exists on one side but not on the other. That's corruption. It's really puzzling. So you can see you've got to get T1 and T2 to be ordered, even though they're independent. You've got to order them consistently on both sides, otherwise you get corruption. And what are you going to do for that? Well, you think I'll use two-phase commit. It's a problem. Users love graphs, but partition graphs are hard. And we can't change the data model because users love it. So we're in this interesting situation where we have to stop corruption. We can't repair afterwards. I've seen some people try to do repair on graphs, but it's impossible, right? Because if a graph diverges, if your shards diverge, and you've got 2, and by definition, the shards are being operated on exclusively legally, then you've got 2 legal graphs. And how do you merge them? Well, you can't, because you end up doing a coin toss. It works in things like Git, because a human has to sit there and puzzle through it. But a computer can't do that. Even in the age of AI, a computer can't do that. So we have to stop corruption from taking hold, which means that we have to coordinate. But coordination limits scalability, right? So there's this bloody trade-off. So we've been working on and off for a few years. We first had the idea for this back in 2012. And it's been bubbling along in the background since then, for this idea of a transaction protocol that would work mostly independently and then coordinate only when it had to, and be able to preserve safety whilst being very scalable. So allowing all servers in a system to accept writes. And we created something called Riot, which is definitely a tortured acronym, which the robot helped me write, and it's replicated independently ordered transactions. I'm going to show you how that works. So there's some requirements for Riot. Scalability seems to be easy. All servers need to be able to participate in processing. Correctness is a bit harder. Yeah, but we know how to do that. We've read the scientific papers on how to uphold various consistency levels. It's not trivial, but we think we can do it. Redundancy, easy, right? Actually, it just means make more copies of stuff. So if you lose one copy, if a computer loses a disk, there's a few more copies of that record scattered around. Practicality, that's hard. It turns out it's really straightforward to build a very complicated protocol that does all these fancy things, but then correspondingly you have really low confidence that that protocol is free of bugs, that it works properly. So we found that was really hard. But what we really took inspiration from was Raft, which made all of the humane decisions. And we thought, could we do this? Could we be like Raft and be humane? But what really turns out is that when you mix scale and correctness, it's extremely hard. Extremely hard. We've seen databases, even graph databases, that have optimized for scale and have sacrificed correctness, which is astonishing to me. Or databases that have had to sacrifice some level of scale to maintain correctness. And in fact, that's where Neo4j is today, right? You can, in extremis, you can surpass Neo4j's scalability characteristics, but you'll never make it give you the wrong answer. But we want the best of all worlds here. And so we've got this thing called Riot. And Riot is a leaderless protocol, which really means, unlike Raft, where there's a single leader that makes all the decisions and everyone else follows, in Riot, anyone can be a leader at the same time as anyone else. So although it's called leaderless, it really means everyone's a leader, or everyone's potentially a leader. And also, unlike Raft, where Raft agrees on a log, a linear data structure, Riot agrees on a tree. Because in Riot, we agree that you and I can be working independently at the same time. And then at some point, we'd like to see that we both agreed that our independent work was accepted. So here we call it a transaction DAG or TX DAG. And here you can see that the universe started when transaction 0 was committed. And then after transaction 0, transaction 1 and transaction 2 were concurrent. And then they committed based on transaction 0. And then transaction 3 committed after 1 and 2 had committed. And then after that, transaction 4 and transaction 6 committed concurrently. And transaction 5 also started its life after transaction 3, but it hasn't finished yet. It's still in the preparing state. So remember, in two-phase commit, we had the prepare and then commit rounds. And we have the analog of that here in Riot. We have a prepare and commit status. And prepare means that we might commit or we might not. Whereas committed means it's a historical fact. Yeah. And so we call the set of committed leaf nodes the leading edge. In this case, it's T4, T6. And that's important because that's effectively a version. You can kind of say, hey, this shard or this database is at version 4,6. And it's for those of you that like your distributed systems, you can squint at that and say, hey, that's a vector clock, isn't it? And I'd lie to you very slightly and say, yeah, it's basically a vector clock. And what's nice about that is we can compare. So if I say, hey, look, my vector clock is 4,6, and you say, hey, my vector clock's 4,6, do you know what? We are at the same state, even though we are different computers, which is kind of lovely. Right, so how does it work? Well, in a single shard, any server can be a coordinator, and that gives us scalability because any client can fire a transaction into the system at any server, and that server will do the work. And we use this metadata, this TX DAG and the leading edge, the vector clock, to determine updates that would be mutually compatible. They don't have to be identical, but they do have to be compatible. And I'll tell you a little bit how that works in a moment. And voting, and there's, and actually we also alert, this is quite a subtle thing, but we also allow learning. So here, if I've got, if I'm at version 456 and you're at version 456, then we are compatible. In fact, we're equal. But if I'm at version 4.6 with 5 preparing, but you tell me you're at version 4.56, that's interesting, because if you're at version 4.56, that means 5's committed. And in Raft, that means committed by a majority, which means it's a historical fact. So the very fact that you told me your version means I can now, without any more coordination, I can upgrade my prepared T5 to a committed T5, and then it actually matches your version identically, is equal. So I'm saying, yeah, now we can proceed. So you can even get that kind of gossip style learning. And then we simplify things just like Raft by saying you can only get a majority. You can only proceed if you get a majority. And in Riot, a typical shard might look like this. All very healthy. You've got a consistent majority and a compatible minority. Probably that minority there, that's a server in Perth, whereas the other two are in Sydney and Melbourne. And you can see what happens there. The speed of light just means that one computer is slightly slower than the others, but all perfectly healthy and normal. Sometimes you can get a diverged minority. They've gotten confused. They've gotten so behind that they can't participate anymore. And that's okay. As long as you have a majority of consistent machines in Riot, you can continue working. So you've got fault tolerance baked in there, right? So I'll show you how that works. You're going to see some UUIDs. Sorry, you're not going to see UUIDs. You're going to see ints, natural numbers. Don't read them as natural numbers. Treat them as UUIDs because, GUIDs in your world. Otherwise, you get confused. So happy path, no fault. Doesn't happen very often. So what happens is that some program, some app that you've built talks to the database, happens to land on server 1 and says, hey, can you process this? Can you store this for me, please? Server 1 says, sure, I'll be your coordinator for this. So I'll ask everybody on your behalf to process this work. And it sends out a prepare message. It says, hey, everybody, could you store this for me, please? It's called transaction 3 and its ancestors, my vector clock is 1, 2. And so it sends out that information to everyone. It immediately votes yes to itself because it'd be insane not to. It sends it out to server 2 and server 3. They can both look at their state where their version clock, their leading edge is 1, 2, see that it matches just fine, and they also vote OK. So you can see here that as soon as server 2's message reaches server 1, we have a majority. Server 3's message will reach server 1 in a few more milliseconds. But we've already got a majority, so we can send out the commit message and commit transaction 3, and then we can tell the client, "Hey, your work's been saved." Right? Easy peasy. But physics is a problem. Independent computers are never identical, at least not physically. So you'd expect some systems to be ahead or behind each other. That's perfectly normal, and you have to tolerate that in these systems. And in fact, because of the cross-learning stuff, I think we can make it work. So this time, notice that server 3, it's the one that's in Perth. It's a bit slower than the Sydney, Melbourne servers just because of the speed of light. So this time, the client issues a transaction, says, hey, could you store this for me? Server 1 happens to be the receiving server in this case. So you do the vote, and server 1 and server 2 are fine, right? They're saying, yep, we have your ancestors, so we're prepared to store this. Server 3 received the message, and it's like, I have one of those ancestors that I've committed, but I do have that other ancestor in the prepared state. So what does it mean? Well, it means I can do an upgrade. On server 3, clearly we don't have exact metadata matches. There's no equality here. But server 3 notices that part of its incoming metadata is that transaction 2 is committed. It's a historical fact elsewhere. It looks in its bucket of pending transaction, the prepared transaction, and says, oh, I've got transaction 2. That means because it's a historical fact elsewhere, it's safe for me to make it a historical fact here. I will move it to committed. Now my vector clock is 1,2 as well, so I can vote commit to this. And so it does vote commit, and you get a commit, even though one of the servers clearly wasn't the same as the others when we started this. If you get a divergent participant, here server 3 has just fallen off the map for a while, it will vote no, and we'll still get the transaction to proceed because the majority were able to vote yes. We didn't fall below our fault tolerance envelope. If we lost another server, we wouldn't be able to process this transaction. Similarly, I'm sorry, not similarly. Once we've processed this transaction correctly, we've committed, server 3 finds out. It says, hey, we've actually committed this transaction that you voted against. And that's server 3, a signal to server 3 to say, hey, sort your life out. You're probably behind. You now need to exit the main protocol and move into what we call the catch-up mode, where you do a copy from some good server and catch yourself up. If you had happened to start the transaction on server 3, which you know is the laggard, that would happen is server 3 would vote yes to itself, but everyone else would vote no. So it's unfortunate because the user's transaction, the user's update isn't going to be processed. But we noticed this divergence, and we stopped the write from happening. So at least now we're not embedding the divergence in our data and corrupting it throughout the rest of time. So it's actually pretty easy. But we had to think a lot about throughput and concurrency. And when we started this work, those vector clocks, those leading edges, we started with the idea that they should be like e-tags on the web. And e-tags are really nice, right? They're a conditional operation. So James mentioned I used to work on REST stuff, and that's where the inspiration came from. And e-tags on the web say, hey, please do this operation if and only if your view of state as represented by the e-tag and my view of state as represented by the e-tag are the same. And so we started off using our leading edges like this, but we found that the whole system would fall into lockstep. And we're like, okay, what can we do here? Well, instead of making things equal, we can make them compatible. And I can say, look, what do I really care about in this? It's not equality. It's that I care that the transactions, the historical transactions that my new transaction depends on, are in my computer and they're in your computer. The other stuff is not so important because we're always going to be a little bit ahead or behind each other. But as long as my ancestors appear locally and on your server, then we can probably proceed. And we can do some of that cross-learning stuff to try and fill in the gaps as well. So when we moved to being compatible, we had a better throughput, although we were still aborting about a third of the transactions even then. And the academics call that a spurious abort. It's work that you spent effort on that ultimately didn't get persisted. But we thought we can actually do something smart here, and it's a bit weird, and it's a bit different to a lot of protocols that we've seen in the past. We decided that unlike two-phase commit and basically everything that followed, where the coordinator is the boss, the coordinator says, will you update this, yes or no? And if everyone votes yes, everyone must now update this. The coordinator has exclusively the deterministic role, the determining role. We decided that in write it should be more of a conversation. So when the coordinator tells you, can you please coordinate? Can you please accept this transaction and with the intent of storing it? That's fine. We send the transaction and the leading edge, and it says, effectively the data plus the conditions that must be met for you to safely store that data. And so then the coordinator does that, but the participants send not only the vote, but they send their leading edge. Actually, they send their leading edge minus the incoming leading edge. We call it a qualifier. But it's really the participant saying, yeah, I will do this, coordinator. I want to do this, but only if you have seen these things that I know about. So it's kind of a cross-check. And it's weird, right? I've got to tell you, it's super weird. If you look in the literature, no one does this. The literature, the coordinator's the boss, the participants are meek underlings that say yes or no. They do not get to qualify their responses. But in Riot, we do, because what we're saying is, hey, I'm the boss. I'd like you to do this work, and I'm at state 1,2. And you write back to me and say, hey, Jim, I want to do this work, but I'm at state 1,2,3. And I say, oh, wait a minute. Have I seen 3? Okay, I have seen 3. It's safe. We can do this. All right. But if I haven't seen 3, it means that as the coordinator, I don't have an up-to-date view of the system, and I shouldn't be allowed to propose transactions because I'm not up to date enough. So you get this bilateral conversation, which means that you bound any possible divergence, right? But you still allow people to operate independently. And so we did a bunch of work on this, including some formal method stuff down at the University of Sydney, so in your neighborhood. And we found that actually you can have all sorts of fun things going on where one server thinks transactions are concurrent because they physically were, and another server, because of just the order, the time of arrival, thinks transactions are serialized. Ooh, formal methods. There's a TLA plus repository for this, rookie. And I will point you to it, or I'll send it over to James and Francis so you can have a look at it. It's quite cool. But what we noticed, you can have slightly different physical arrangements of the data locally that are globally compatible. So here, transactions 1 and 10 on server 3 were seen as being concurrent because of the arrival order. But on servers 1 and 2, they were serialized. And that's okay, right? Providing there's no underlying contention of key access, that's perfectly reasonable. And we allow in Riot for this to happen. We don't have to be that strict when there are equivalent orderings are permitted because it gives us scalability. Now, it turns out that's the hard stuff. The single shard stuff in Riot is the hard stuff because there's all these leading edges and vector clocks and all that stuff. Making Riot scale across shards, it turns out, quite to our surprise, is completely simple. And all we do is have a system like this. So in this case, just 2 shards. Again, any server in any shard can act as a coordinator. And the only rule is within shards, you need a majority. But if you're transacting across shards, every shard involved must vote yes for a transaction to complete. And we call that conjunction of majorities. So every shard must vote yes, but within a shard, you only need a majority as a minimum. And what happens is you have shards like this, where there are things that are ahead, are behind. You can get a positive outcome from that, or you can have things like this. Here, one of the shards voted no, so even if every other shard had a complete unanimous majority, this transaction won't work. The way that we engineered this is that we use a piece of magic called interpose coordinators. Which is weird because I haven't heard of these things since I was a young person. In my first job out of grad school, when I was working on middleware, we had these things, and I've not seen them since. But interpose coordinator says, look, I'm a remote agent for you, and my job is to coordinate locally, and I will tell you the results of that coordination so that you, main coordinator, don't, for example, have to send lots of coordination messages across the WAN. Effectively, I'm a local aggregator for you. It doesn't change the outcome of everything. It just means there are fewer messages over the slow network. And the way it works is something like this. So now these aren't servers, they're shards. Shard 1 happened to be where the transaction started. And it, as part of its work, enlisted a machine on shard 3 as its local coordinator, its interpose coordinator, and said, hey, can you coordinate this update for me on your shard and then tell me the results? It then went back and coordinated its own shard. And if both shards said yes, then you get the transaction committed, else it doesn't commit. So that's really easy. The sharding stuff, the stuff I thought would be really hard, turned out to be simple. And the stuff I thought would be simple, getting it to work on one shard, turned out to be the complicated bit. Go figure. Does it work? Is it useful? It turns out yes. So this is an evaluation integrating into Neo4j. The red circle there is interesting. It's the kind of normal number of clients. So we did. I asked the Neo4j cloud guys how many clients is typical connecting to an individual instance of Neo4j in the cloud, and it was basically less than 100, and 100 was very much at the tail end. So if you look at the kind of normal spot where people connect, because it's typically an app connects to middleware. Middleware has a pool of connections that connects to the database. For low numbers of connections, Riot is much faster than Neo4j, which is nice. As you get more connections, as you get 1,000 connections, a pathological number of connections, Neo4j's Raft implementation is faster than Riot. And that's a bit weird at first, but then you think about it, you've got one server making all the decisions, so it can make them fast. Whereas in Riot, all these servers for 1,000 concurrent clients have to talk to each other, so it slows down. So it turns out that Riot's good for a normal use case, but if you've got a pathological use case where you have 1,000 concurrent users all absolutely hammering the database, A leader-based system is going to be faster, which is weird. But what is perhaps lovely is this one. The blue line is the throughput of Riot. The orange line is the throughput of Neo4j with Raft. And at about 20 seconds, we killed the leader. It's perfectly fine. Machines die all the time, especially in the cloud. So a machine died, and then Neo4j's throughput went basically to 0 and didn't recover to its normal levels for about 20 seconds, right? That's horrible. Now, you might say, Jim, how often does this happen? And I'll tell you, it happens about 1.4 times a day, which is not a lot. So once a day, basically. But if that's Black Friday, 20 seconds worth of sales is a big deal. Whereas Riot, because it doesn't have a leader, if you kill a machine, sure, the transactions that were in flight on that machine die, you have to replay them. But no one stops working because you don't need a leader. So you carry on processing. So you've got constant processing in Riot, which is a really nice outcome. Turns out traffic is higher for Riot, as you'd expect. It's a distributed decision-making engine rather than a centralized decision-making engine. A lot of that comes from transmitting large leading edges. And it turns out we've got a little experiment that I'm about to run where we're going to gzip them. And we think this, just gzipping the leading edges as they get large, will eradicate this. Latency of Riot, for reasonable cases, up to about 100 clients, latency is good, comparable with Raft. A little bit more variance, as you'd expect. And in the pathological cases, the variance is high, as you'd expect. But in normal cases, Riot comes out pretty well, it turns out. Now, there's a bunch of people that were helpful in developing this. If you're interested, rookie for you and Ian, Junhao Hu was a honors and now master's student at UCID. He wrote the TLA Plus stuff for this. So thank you to Junhao, Michael, and Alan down in Sydney for helping us on this. And the rest of the team here who have been pitching in over the years. If you're wondering about the photograph, it's AI slop, but it is an accurate representation of a high school in the English Midlands circa 1990, where somehow some kid managed to write a placard with the words "Full Riot" on them, put it in the window, and induced everyone else in the adjoining science block to also have a full Riot in their classrooms, which is an embarrassing fact. I can't believe I'm a scientist now. So that's why, really, I just wanted to, after all these years, I wanted to call something Riot to commemorate the brave act of full Riot in that high school in the English Midlands. I know, right? It's embarrassing. So that's me. I hope that was a useful use of your evening. I'm really happy if you got any questions, if you want to bam them up on the chat. I'm scanning through. Question to Jim. In practical terms, which described protocols are being currently used on prod? Okay, sorry. Thank you, Nose Ratio. We see a lot of Raft, right? Raft is extremely popular. It underpins a lot of databases. Google, because they're different and they're Google, they could use Raft. They're quite aware of its existence, but they're so smart that they tend to use Paxos. And you will definitely find, particularly in the depths of some of your big four banks, there will be big steam-powered machines that are still running two-phase commit in very narrow bounded contexts. They're the big ones out there. And look, there are dozens of other protocols. And when you're writing this stuff up, we've written this stuff up for Sigmod and it's being accepted. But it turns out there are dozens of other protocols that do this kind of stuff, and none of them are really in broad use. And by the way, neither is Riot in broad use. We are experimenting with it at Neo4j. But before we can really, kind of deploy it widely, we'd like to see some feedback from the research community and the practitioner community. But when you talk about Visa, MasterCard, and so on, these systems are complicated. There'll be parts of these systems that are coordinated via these protocols, and parts of these systems that simply won't, because the cost of coordinating like a stream of transactions is too high. So they will tend to do things like, oh look, we'll make it durable, and we will like jury rig some kind of idempotency scheme with a GUID. And for us, because the processing window is short, at seconds, we can get away with it. So they're able to build their own specific infrastructure for their own needs. So it varies, but if you're in database world, as I am, Paxos and Raft and two-phase commit are very popular, and other ones aren't. Scrolling up if there's anything else. Binary tree. Martin Kleppman, all good.
So, Jim, are you planning to redevelop the Raft implementation into a Riot implementation at Neo4j, or have it as a config option to switch between, or something along those lines?
Probably the latter, because we really like the Raft implementation. So I was on the team that built that Raft implementation, and I'm quite proud of it still, because it was quite a cool project to be on. Ultimately, in the short term, Raft is king because it's well understood. It actually has really good throughput characteristics. The only thing that we don't like so much is the kind of jitter when you get a leader election. But otherwise, Raft's really good. And for most people, Raft is good enough. But what we're noticing is that these AI workloads are being quite demanding about the size of graphs that we want to store, particularly nowadays where there's this idea of context graphs, where literally the decision traces of the AI are going to also be stored in your graph, along with your kind of knowledge graph data and blah, blah, blah. And that's really the thing that's driving us, because we see the right throughput requirements for that are going up and up and up. So we want to be able to meet that. So I think from a product management point of view at Neo4j, this is definitely an option for us in the longer term. I would imagine, although it's not my place to say, I'm not a product manager at Neo4j, there would effectively be two versions for a while, because the Raft implementation is so mature and solid. Why would you throw that away? And there'd be a kind of a version for the 1%, which is kind of on this newer tech, and it's probably got a different pricing structure and all that stuff. But I think you'd run concurrent for a while, until such point where you say actually one of these is legacy, and then you do the responsible retirement thing and move people over. But that's not a short-term thing. That's not a 2026 thing for sure. It probably isn't even a 2028 thing, because that, as I said, that Raft infrastructure is so mature and good that we'd be reluctant to bin it.
Thanks, Jim. I think we've got a couple more there questions. What have we got?
Some good ones. There's Ian and George and Rookie again. Okay, I'll do Ian. Since large scale routing graphs, relatively custom graph. Blah, 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 blah. Okay, this is more of a Neo4j thing, so I'll address it. Ian, the answer is probably. Neo4j is a very general purpose graph database, and so possibly, although probably you've got some high performance C++ implementation that does your job really well, and why bother rewriting it in Neo4j? If you are in the mood to kind of do databasey stuff, Neo4j comes in two halves. There's the kind of database half, and then there's the complementary compute engine that work together in harmony. But effectively, you can say export, project this subgraph into the compute engine, and you can run things like pathfinding and optimization in the compute engine. And then if you want to, you get that written back into the database. Having said that, if you've got a high performance implementation that you're already happy with, then then please ignore Neo4j for now. George, you were next. How do these methods compare to blockchain protocols? Excellent observation. Similar, right? Although we in database world, we laugh at the blockchain because it's trying to do the same thing, right? You've got a bunch of people that are all trying to write to the head of the blockchain, and you have to coordinate it in some way. And so the blockchain does that very slowly. It's extremely high energy cost, but it's basically doing the same thing. And where the blockchain can do something like 7 transactions per second, on a Raspberry Pi, I can do 7,000 transactions per second. Really, the difference is that in Neo4j, because the cluster, we assume that it's trusted. We don't assume any Byzantine actors in the cluster. We can optimize and do lots more transactions per second at lower carbon cost. Whereas the blockchain, you assume everyone's an asshole. And so the coordination is necessarily more expensive and slower. Unfortunately, that's one of the reasons why we could never really make blockchain work for, buying a packet of chips, because the transaction cost is too high and too slow. But you're right to observe that they are at least things like Paxos and Raft are very similar to the blockchain. In fact, if you treat the blockchain as a log, Raft maps quite cleanly onto it, and the database people know this, and we point and laugh. All right, Rookie. Could there be some revolutionary breakthrough that makes distributed consensus easier? Don't know about revolutionary breakthroughs, to be honest. If I did, I'd be a rich man. But I do know about evolutionary breakthroughs, which is making distributed systems, if not easier, then certainly faster and perhaps more practical. Weird things are happening in hardware, and like it's a sort of I feel a bit sad because I guess like many of us, as a youngster, I used to build PCs and I was really into hardware. Like I was really, really into it. Like I knew my DX33 from my DX266. So you can age me now. And then for a while, hardware got really boring, right? I think like the post Xeon, everything was just a box with Intel chips and some gigs of RAM. And it got boring. And it was even boring in the early days of the cloud. It's like, yeah, here's a box that you used to have in your office. It's now in my data center. But then hardware got interesting. I don't know if you noticed, but like in the last half decade plus, hardware got interesting, different kinds of chips. Hey, I've got an ARM CPU, I've got an Intel CPU. That's interesting. But perhaps more interesting is the explosion in different kinds of hardware, things like GPUs, CPUs, blah, blah, blah. All interesting. But what I think is really interesting is FPGAs. FPGA is a field programmable gate array. They've been around for like decades. I had a mate when I was doing my PhD was working on them back then. And what it really means is it's programmable hardware. And that programmable hardware now is finding its way into motherboards on computers. And it means that you can do things like program it to do a specific operation really fast. So there's a startup cost where programming the FPGA is quite expensive. But once you've programmed it, effectively, you've got custom silicon. And you could use that to do things like, I don't know, matrix multiplications or factorizations or something. In my world, you can use it to run database operations. And that's interesting when it's on a computer. But these FPGAs, they're starting to turn up in remarkable places. FPGAs are now on disk. They're on your SSD. So actually, for me as a database person, I could program like a search or sort to run directly on the disk. I can dispatch it over there as a subtask. It runs on the SSD, gives me back some records. Better, I can also, these things are turning up on network switches. So as a distributed systems person, it's quite feasible for me to take part of Riot, implement it on the network switch closest to where the servers are, and have Riot coordinated over there and just send me results back that I need. So I think, evolutionary, we're starting to see the rise of very widespread quasi-universal programmable hardware, and I think that's going to be very interesting. It's going to speed things up. It's going to mean we've got more moving parts, so we have to figure out patterns for how we can deal with fault tolerance in those moving parts. But the cloud is suddenly getting very interesting. It's no longer just a computer that you could buy being rented to you for maximal profit. It's getting really fascinating. All right, I don't see any more questions. James, do you?
No, I think you've answered them all. So let me cue the applause, which I just worked out to do here. There we go.
Well, that's a lovely way to start my day.
That's right. Poor you. We're just going off to bed, and you're studying. We're going to.
I don't think you're not going off to bed at 8:20 p.m. surely.
I've got a cold. I might be actually.
Oh.
No, kissing the kids off to bed, I think, next. But yes, thank you very much, Jim, for the talk and for making some very complicated topics understandable and approachable for us.
Absolute pleasure. Thank you for inviting me.
And we have some giveaways as well. And Francis, do you want to say anything before the giveaways?
No, just good luck, everyone. I know everyone's dying to win those Jeff Rains licenses.
All right, so we are getting kind of late, so I better get into it. So let's see. Let's start with an easy one. So what's a problem with using two-phase commit? This is for a JetBrains license. Yes, first answer in the chat wins. Francis isn't allowed to win. His answer never wins either. There you go. Lord Teaspoon, JetBrains license, coordinator of the single point of failure. You happy with that, Jim?
That is my answer as well, and I know I'm also not allowed to win. So that I would have been with Lord Teaspoon.
Oh, fair enough. That sounds good. Right. You do need a license, don't you, Lord Teaspoon? Otherwise, we can maybe swap conference tickets or something later, depending on who else wins. All right. Next one. So a bit harder. So this one is for a conference ticket. So tell me, what were at least one, if not two, benefits of Paxos over the two-phase commit? If no one gets the answers, we'll give them all to Jim over, I think. Sorry, I've got kids in the background there, if you can hear them.
Please don't subject your kids to Paxos.
At least what was one of the benefits of Paxos over the two-phase commit, or what was something that was an important change about the coordinators? Oh, hang on, someone's got that.
Oh, I think so. I think that's the answer I would want. Coordinators a role. Yeah.
That sounds good. All right. Hey, Coot. Both of you who have won, send me a meetup message if you don't have the email, with your email address, so that I can sort out the prizes for those. Sorry, Lord Teaspoon, about your ADSL there. But there are more questions, so don't give up yet. All right, so let's go to a JetBrains license again. So for Raft, yeah, what was the big benefit of Raft over Paxos? You're not allowed to give a correct answer, Jim. That's bullshit. Are you happy with Lord Teaspoon's answer for understandability?
I want to hire Lord Teaspoon into my team.
Well, there's remote work, right?
That's what we've always called you.
All right, so we'll take Lord Teaspoon's answer then for understood. I think at this point maybe don't answer the last question, Lord Teaspoon, because you've got one license and one conference. Let's see. Put in Swiss license. Yeah. Oh no, hang on. That was actually going to be a JetBrains, but maybe we better make it the conference since Lord Teaspoon won. Oh man, I'm losing track of things. Obviously, too late.
We need coordination, James.
Yeah, there's not even a two-face commit going on.
Yeah, I think you have to roll something back, and we'll have to start again. No, so Lord Teaspoon, I'll give you. So we've got the we got K Coot with the ticket, right? And Lord Teaspoon with the ticket and the conference. Sorry, I mean the man. Obviously not following Jay. All right, Lord Teaspoon with a license and the conference ticket, and K Coot with a conference ticket. So that means we've got one prize left to give away, which is the Riot question on Riot. So this is for a JetBrains license. So how many leaders are there in Riot? This is possibly a trick question.
I think there are two possible answers to this that are acceptable, and none of them have been surfaced so far.
I didn't have, with 4 giveaways, I didn't have many extra questions, but I can make one up, I guess, if no one's, or I asked him for a question, actually, if no one comes up with this one. Come on, how many leaders in Riot? Maybe Riot's too hard to Google.
Oh, Lord Teaspoon, like, we should talk. You need a job. You need to come to Neo4j. Yeah, thanks.
All right, we're going to give the winning to Juan. You happy with that?
Yeah, absolutely. Everyone can be a leader. So Francis was right. Lord Teaspoon was right. Yeah.
We can't give
The
them
answer is 0 to all.
All right.
But 0 is not a very good system, right? Because then no one's doing any work.
All managers. All right, very good. I think we've got all the prizes now. So we've got Lord Teaspoon with a license and a conference ticket, K-Coot with a conference ticket, and Juan with a license. So if I've got this wrong, please quickly comment in the chat. Otherwise, that's what we'll go with as consensus, based on a vote of me only. Let's see. All right, let's assume that's correct. All right. Well, thank you again, Jim, for spending your early morning with us and talking to us about all this.
It was a pleasure. Thank you, everybody, for tuning in. It's been lovely to spend time talking about this.
So yes, some few thanks in the chat, and yes, if anyone wants to present, we've got a few talkers, a few speakers lined up. Man, sorry guys, I'm obviously not at my best tonight. Yes, a few speakers lined up, but still room later in the year if anyone would like to speak. So yes, drop us a message or email or whatever if you've got some topic you want to talk about.
Just quickly, I think next month we're aiming to have a hybrid event, so we're going to be in person and also streaming as well. So we'll probably be at the Mantle group. Just a heads up.
Yes, that's right. It's AI on big legacy code bases next month in the Mantle group. So yes, stay tuned for more info about that one. But yeah. All right. So thanks very much, everyone, and good night. And we'll see you all in person next month, hopefully, or maybe some of you online as well. Speak to you later. Bye.
All right. See you guys.
Bye.
Bye.